Hello everybody, this is a course on metaheuristics in optimization and I am Aditya Chattopadhyay from Department of Statistics, University of Calcutta. Now you all know about what is optimization. Suppose I have a function f and this function is a function of a single variable x, f(x). Now I want to optimize it. So what do? I get the classical calculus approach, and what is that approach? I want to find the first derivative of f(x), say f dash x, equate it to 0, solve that equation to get the steady state solution or fixed point solution, and then judge for the convexity of that function f(x) in terms of second derivative of f(x). Now, suppose we are considering the why I am talking about convexity, suppose I am considering the minimization problem, and that is why this convexity comes. And what do then? To get the second derivative and then evaluate that second derivative at that point already obtained as equilibrium solution or steady state solution, and if that is more than equal to 0, I have a minimization problem solved at that point. Now, let us go from a single variable case to multivariable case. Suppose I have several variables x1, x2, xn, function of several variable, and I want to get partial derivatives of that function with respect to that variables x1, x2, xn, and equate all these partial derivatives to 0. I now have n equations. We solve these n equations simultaneously, get a vector of solution which is known as again the fixed point solution, and then to judge the convexity of that function we go for evaluation of the Hessian matrix, that is the second derivative matrix, and that second derivative matrix is evaluated at that equilibrium point solution or fixed point solution, and we judge for the positive definiteness of that function. Previously it was more than equal to 0, now we go for positive definiteness of that matrix, and if that matrix is positive definite, we get a minimum at that x1, x2, xn solution. So, this is the classical calculus approach. Now, next comes the problem of constraint optimization problem. I have to optimize the function f(x) with respect to, and suppose this f is a function of several variables x1, x2, xn, and suppose I have to optimize it with respect to one single constant, say gx equal to 0. Now, what do then? I compute the Lagrangian function L given by f(x) plus lambda gx, and then go for this usual calculus approach to solve this and get the values of x, and that is what is known as constraint minimization problem. Now, I can have several constants. So, I have the function f(x), a multivariate function, and our constants are now, suppose I have m constant g1, g2, gm, then and all these are equal to 0, then I construct the Lagrangian as f(x) plus summation lambda I g I x, where lambda i's are the Lagrangian multiplier, and again we solve for this by getting the first derivative, second derivative matrix, etc., etc. So, these are the issues of optimization problems, either in the usual unconstant setup or in the issue of constant setup. Now, let us consider a typical optimization problem, what is known as linear programming problem. Now, in a linear programming problem, we do not do this thing. We do not go for Lagrange multiplier, we have a linear function and we have to optimize that linear function, say z equal to summation c I x I ranges from 1 to n. Usually we write it as C transpose x, and I have the constraints, again linear constraints A x equal to b, where A is the coefficient matrix. X is usually in any optimization problem is known as decision variable, and x is a vector, and this b is the requirement vector. So, A x equal to b, that is my constant, and then I put an additional restriction x more than equal to 0. That means, my solution should lie in the positive orthant of the n dimensional real space. And then in a linear programming problem, how do I proceed? We do not go for this Lagrangian technique, we do not go for this thing, because it is a trivially convex function. So, what do I do then? I go for a basic solution, and how this basic matrix is obtained? The basic matrix comprises of the linearly independent columns of A. I compute that basis matrix B and a basic feasible solution x b, x suffix b. So, b x b equal to b, this is my now the equation of the constraint, and I go for this b is a full rank matrix. So, I can invert it. So, x b equal to b inverse b, this gives me the basic feasible solution. And there is a celebrated theorem which gives that all these basic feasible solutions corresponds to the extreme point of the convex set of feasible set, because the feasible solution is the solutions which satisfies the constraint with that additional restriction x more than equal to 0, and this set is a convex set. I move from one basic feasible solution to the other basic feasible solution in the celebrated simplex algorithm developed by Danzig, and then I evaluate the corresponding net evaluation, what is known as Zj minus Cj. I check for whether all of them are less than equal to 0. Remember, I was considering a minimization problem. So, Zj minus Cj less than equal to 0 is the condition for optimality for all the variables, and then if that is not satisfied, we go for one basis to another basis. There are rules of that, there are exit criterion, there are entry criterion, and ultimately we get the solutions. Now, what is the common in all these approaches? That is what I am going to talk about. So, we have three facets of algorithm. The first one is rule for initial choice. In any optimization problem, you start from somewhere. Suppose a basic feasible solution is the first basic feasible solution or initial basic feasible solution is the rule for first choice. In a say a calculus technique, we do not have this kind of problem. I do not have to iterate, because I have another technique, but suppose I have an iteration procedure. So, I go for some solution and then go for trying to get a better solution. So, that is the idea of algorithm. So, one thing is rule for initial choice, and then we go from one basis to another basis. So, that means we have there is a certain definite rule for moving from one set of solution to the other set of solution. So, that is the second point. So, moving from one vertex to the other vertex, that is the idea in simplex algorithm. Suppose I have an iterative procedure in any other optimization problem. I go from one solution to the other solution, and I check for optimality, whether this solution is better than the previous one or like that, and then I take a decision whether to move or not. And if it is a minimization problem, in each iteration you are going towards the goal. That means, you are going to the minimum value and not further from the goal. That means, in each iteration we are not getting a worst solution. So, when in each iteration we are not getting a worst solution, that means, we are having a minimum value, I mean a sequence of solutions having objective function say less than equal to the previous one, less than equal to the previous one. So, this type of algorithm where I have always go for the best, this type of algorithm are known as greedy algorithm. So, simplex algorithm in that sense, loosely speaking, is a greedy algorithm. And in metaheuristics optimization, I will later show that this greediness we have to overcome, because we need not have to greedy, because if we become greedy, there is a possibility that we get stuck in a local optimality. I will come to that, but first of all the last point of that thing, and that is what is known as stopping rule. Stopping rule means there it was net evaluation less than equal to 0. I need to have some stopping rule, and this stopping rule might not be that evaluating this. In fact, if I do not have sufficient amount of improvement in the solution, I can have a stopping rule. So, I stop somewhere. So, I repeat, the three facets of an algorithms are this. Number one, I should have a rule for initial choice. Number 2, I should have a rule for movement from one solution to the other solution, and thirdly there should be stopping rule. Facets are that from where to start, how to proceed and where to stop. Now, we define an optimization problem, general optimization problem. So, I have to function f, this is a multivariable function and this is defined in capital X, capital is the set of feasible solutions and S is the solution space. So, capital X corresponds to the solutions which satisfies the constraints. So, it should be a proper subset of the entire solution space S, and I have to minimize that function. Now, what is the important thing is, if I have this S, that is the solution space finite but large, then a combinatorial optimization problem is defined. And if S is the entire real space, n dimensional real space, then I have the continuous optimization problem. So, for a combinatorial optimization problem, I should have this finite but large solution space. And how do I define a solution or optimal solution? Optimal solution is, I have an x star, this belongs to this capital X set of feasible solution, and I should have f x star less than equal to f x for all x belonging to that capital X. Okay? And then my stopping rule. There might be two stopping rule, two types of stopping rule. One is the absolute stopping rule, that means if I have margin of error is epsilon, then I stop at this x star if this is satisfied. Otherwise, I may have a relative stopping rule, I should stop at x star if this is satisfied. So, these two are the stopping rules I define, or you may have stopping rules say I have this number of iterations done, and depending upon the number of iterations I can suggest a stopping rule, or a stopping rule is if no further improvement is noticed, I will stop here. Now, what are the computational issues? The computational issues are, first, the time needed to do all these things should be limited, should be finite. You do not have infinite amount of time to solve a problem. And secondly, you require only the functional value. Sometimes you are not provided with the analytical functional form of f x, it might not be there. I just can compute the value of the function at certain x. So, you require this, and this kind of problems you have to encounter in real life, and here comes what is known as heuristics. So, why it is heuristics is required? First of all, the practical instances, the problems are very complicated. So, you do not have all these things are there, you have sufficient arsenals in your bank to encounter this type of problems, but still you cannot solve it. There are real life problems which are very difficult and exact solution is out of question. And there is second point is, it is complexity theory, because if the problem is NP hard, then you cannot solve it in a finite amount of time, even it is known as polynomial amount of time. And if it is an NP complete problem, then also there are algorithms which may not be applicable to solve these things. So, what is the way out? Way out is you have to go for heuristics. So, that is the requirement for heuristics. And what are the advantages of heuristics? The advantages of heuristics are, it assures a worst case guarantee. That means, you are not getting a very bad solution, that is the first point. Second point is, heuristic addresses the following. First of all, avoid excessive computation, and secondly, they get rid of this local optima. So, I am coming to that, get rid of the local optima. So, what is an local optima? Local optima is something like this. I have local optima here, I have local optima here, but the actual global optima here. Okay? So, this is the idea. So, these are the local optima and means minimum, and this is my global optimal. My objective is to reach here, but I can get stuck here or here. So, my heuristic should be such that I can avoid those valleys, this valley or that valley, because if I get stuck in this valley, then I never reach this point. So, that is the idea of heuristics. NXL is the neighborhood of XL, that is the local optima, and a point is, so there are several local optima. Suppose I have a local optima here, I have a local optima here. So, you may suggest that if I take an average of this local optima, I will get the global optima, but that is not true, because optimums are here, but the actual optimum is something here. Okay. So, you cannot have an average local optimal average to give you a global optimal. I can start from somewhere, I go to one optimal. I can start from another point, I move to somewhere, but this somewheres may not be your global optima. So, that is the point, and that wise you require heuristics. Okay. So, what are the popular meta heuristics? The popular meta heuristics are, I am going to discuss the first two, variable neighborhood search and simulated annealing. There are others, several lists of others, but what are the criticisms? The first point is, one heuristic may be adequate for addressing one kind of problem. There is no such thing. So, no single heuristic will work well in all problems. That is the first thing. Second thing is, most of them are based on certain metaphors, say behavior of insect, musicians playing together, something like that. So, physical metaphors, and that is why nowadays they are saying, the experts are saying that you can develop heuristics, but please be aware that heuristics which are very close to genetic algorithm or taboo search or simulated annealing, they are going to, the scientific community is going to accept that thing. So, I am going to the first kind of heuristics that I am going to talk, that is VNS, variable neighborhood search, and VNS was practically first developed by this person Mladenovic, and interestingly this paper by Hansen and Mladenovic appeared in European Journal of Operations Research. That is possibly in the history of European Journal of Operations Research, this is the top 10 downloaded paper or top 10 cited paper published in European Journal of Operations Research, a very popular paper on variable neighborhood search. And this VNS is a meta heuristic which systematically exploits two things. One, in the descent to local minima, that means you go for local minima, but you avoid local minima, and then in the escape from the valley. So, you descend to local minima, but you do not get struck to that local minima, you go to escape from that local minima to reach the global minima. This variable neighborhood search practically depends upon three facts. Fact 1 is a local minima with respect to one neighborhood need not be a local minima with respect to another neighborhood. That means, a local optima here and a local optima here, they might be different. This is the number one fact. Second fact is a global minima. That means, suppose I have a global minima somewhere here and I have local optima here, local optima here, local optima here. So, a global optima should correspond to the local optima with respect to all the neighborhoods. So, all the neighborhoods collected together, this gives you the global minima. And thirdly, for many problems, local minima with respect to one or several neighborhoods are relatively close to each other. One neighborhood here, they are close to each other. And naturally, what is the consequences of these facts? These facts are, if you have an idea of the local minima, that is the important observation, that is the most important. So, last observation is empirical, local optima often provides some information on the global optima. Now, how do I implement a VNS? So, I start from an initialization, so initial solution x, I have a neighborhood nkx, this k stands for the level of neighborhood, choose a stopping condition, say minimum number of iterations, and repeat these three steps. One is until k equal to k max, that means up to all levels of neighborhood, you first go for shaking. Shaking means generate another solution. So, generate a point x dash at random in the neighborhood of n k x k equal to 1. So, n 1 x first set of neighborhood. Then local search. So, apply some local search method and then move on not. Then if you accept whether you want to move or not. So, if this local optima is better than the incumbent, that means suppose I have a solution which is better than the incumbent one, then move that. So, x dash is replaced to x, but if it is not so, then I do not go do that. And the point is, when I replace this, I go for this n 1 double x dash. So, I repeat this thing and go for the second level of neighborhood, third level of neighborhood, like that, and ultimately I have certain stopping conditions, say total number of iterations. So, it is very simple algorithm, looks very simple, but implementation is requires high dose of computation. Okay. Now, I go to the second meta heuristic, that is simulated annealing, and how do I implement it. Now, what is annealing? Annealing means cooling. So, a temperature inside a substance is because of the movement of the particles of the substance consisting of the substance. So, when you have a cooling schedule, the movement of the particles get reduced, and the equilibrium position is when this temperature reaches absolute 0 or close to absolute 0. And this is what is implemented. This is a physical property, and this has been applied in this simulated annealing implementation. So, I have two loops in the computation. First of all, inner loop. In the inner loop, I get a current solution x and define a temperature usually very large, T more than 0. Step 1, propose a new value x dash in the neighborhood of x. Then step 2, accept x dash. That means you accept x dash as a better solution always, but you may accept a worse solution with certain probability. So, that is the basic idea, and in that sense we are not greedy. Okay. So, accept x dash as a new solution with probability this. What does the consequence? Consequence is if f x dash is less than f x, and look, remember I am considering a minimization problem. So, f x dash less than f x means this becomes positive, and this becomes positive means this becomes more than 1. So, minimum value of 1. So, if I have a better solution, I always accept, but if I have a worse solution f x dash more than equal to f x, so I have this thing negative, then e to the power of this thing is something less than 1, and you choose, that is the probability. So, that is the probability to choose a worse solution. So, that is the beauty of simulated annealing. You are accepting a better solution, but you are also accepting a worse solution for the time being. So, for the particular temperature, and you go on computing these values, you are doing these values for a particular temperature. Observe that if T goes to infinity, that means temperature is extremely high, this thing is 1, that means you always accept a solution, and if T goes to 0, that means everything is cooled down, you are not going to accept it. P x to x dash is not equal to 0, exactly equal to 0, and this is the inner loop, and the next point is outer loop. So, outer loop, what do I do then? I reduce the temperature. So, instead of T, when no improvement in the inner loop is found, instead of T we go for Kt, K is something less than 1. So, we go for Kt and do this, restart the inner loop, and we stop when to stop, stop when I have T goes to 0. Now, what is the actually what is being happening in a simulated annealing? So, first thing is I have a starting solution, that means the initial value or initial temperatures are there. Then how to proceed? I am accepting a good solution, but I may accept a bad solution. So, the choice of the neighborhood, that is also one factor. Acceptance rejection, that means there she is an acceptance rejection mechanism, and where to stop, that means how to stop when T goes to 0, the cooling schedule. So, all the features of algorithm are preserved here. The physical significance of simulated annealing, it has a close connection with Markov chain. Okay. So, for a given T, I have a homogeneous Markov chain, and for variable T, I have a non-homogeneous Markov chain. This is the first point. And you might be knowing about an algorithm given by Metropolis Hastings Markov chain Monte Carlo algorithm. Practically, this is an algorithm to generate samples from a distribution, what is known as target distribution. And what you do is, you try to construct a Markov chain having stationary distribution as the target distribution. And if you construct, or if you have been able to construct that Markov chain, then if you sample from the Markov chain, then you are having a sample from that distribution. So, that is the basic idea of Metropolis-Hastings algorithm, and in fact that is practically what is happening here. Okay. So, why cooling schedule gives you the answer? The answer is, first of all, this x t generated by simulated annealing is a Markov chain, and this Markov chain is a stationary distribution of the Boltzmann distribution. This P t x proportional to this is the Boltzmann distribution. And how do you interpret a Boltzmann distribution? If you maximize the Shannon entropy with respect to the normalizing constant summation p equal to 1 and mean entropy equal to certain fixed value, we get Boltzmann distribution. So, Boltzmann distribution is my target, okay? And you generate this thing Metropolis-Hastings Markov chain Monte Carlo method, and this is practically what is happening in simulated annealing. The best cooling schedule given by Gaiman and Gaiman is something like this: T t more than equal to T naught by log of 1 plus T, that is your k choice of k. If you do this invariably or practically, you do not get the optimum always, as I said, that because you may not have a proof for optimality. So, but you are getting a solution, you are practically having a distribution of the solutions, and suppose the mean of the distribution or the mode of that distribution gives you the solution. So, you have a distribution of optimal solution, it is not an unique optimal solution in both variable neighborhood search and simulated annealing. Now, you all know about travelling salesman problem, and travelling salesman is an NP complete problem. Simulated annealing or this variable neighborhood search can solve this problem with a limited computation time. So, that is the beauty of this. And then what are the desirable properties of metaheuristics? I have listed some, these 5, and afterwards I have 6. So, in all 11 metaheuristics properties. These properties practically tells what I have taught, I mean what I have talked about. So, what are the desirable features of metaheuristics? And for some selected bibliography, I am giving you something. The first one is the first paper on Markov chain Monte Carlo. Metropolis is the key author. Hastings, this person gives you the algorithm for asymmetric thing. This is the practically the simulated annealing paper. Hansen and Mladenovic, this paper I have talked about, European journal. This is a review paper, and lastly I am talking about this paper, I mean this book. This is a book on computational statistics. So, I hope you will be my lecture will be useful to you to understand what is metaheuristics, and thank you all.